Okay, let's move on to the next other type of supervised learning technique we're going to discuss in this course, classification. Okay, so the classification problem is very similar to the regression problem. Again, as inputs, we have measurements x1 through xn. These are coming into us in some input space, and you can just think of that as being Rd. And then we want to predict the output that corresponds to the input. So for each x coming into us, we want to predict a corresponding y. Except in this case, the y associated with an x is from some discrete output space that assigns x to one of k possible classes. So there's no relationship between the numbers. If the class is 1 versus 2, that doesn't mean the second class is 1 greater than the first class. There's just an indicator of a group that x belongs to. So for example, for something called binary classification, we would want to predict, we would want to assign an incoming x to a class either plus or minus 1 or plus 1 or 0, according to which of the two classes that observation belongs to. You can think of spam email as an example. If the input is an email, we would want to categorize or classify that email as being either spam or not spam. And so the input would be the email, and the corresponding output, the y, would be a label of spam or not spam. For multi-class classification, we simply have multiple classes. So for example, k-class classification problem would assign the input to one of k possible groups or classes. So as with the regression problem, we need to define what a classifier is. So classification, a classifier is just a function. Just like the regression problem, we defined a function. With classification, we'll define a function as well, except this function is going to map the input x to a class. So we'll take as an input to the function the x, the email, for example, and the output is going to be a label or the index of which class that input belongs to. So as with regression, this problem is twofold. First, we need to define what the classifier is. We need to define what is the function that we're going to use to assign inputs to outputs. And also, we need to then learn the actual classifier. So the classifier that we define is going to have unknown parameters, and we need to then learn those parameters using labeled training data. So we would consider pairs of labeled points in our training set labeled data in this case. Okay, so let's look at the simplest classifier that one could come up with, the nearest neighbor classifier. Okay, so here's an example of a nearest neighbor classification problem. So as input, I'm showing data in R2. So each of these points corresponds to an input x location. And then the corresponding label for this data set is shown as the color assigned to the points. So for example, this is a two-class classification problem. All of the points that are colored blue belong to one of the two classes. We call it class 0. And all of the points that are colored red belong to the other class, call it class 1. And so now our goal is for a new input point, x, we have the new location. We want to assign that x to one of the two classes, meaning we want to know which color should I color this dot as, red or blue. So the nearest neighbors, the nearest neighbor classifier does this by simply finding the point within our labeled data set among all of these colored points, finding the point that is closest to the new input point that we want to classify, and then assigning the class of this input to be whatever the class is of the nearest neighbor. So for this example, the new point that we wish to classify is closest to this point here in our training data set. This point is labeled class blue, and therefore we would say that this new point we will predict is going to be also class blue. So it's a straightforward classifier. The first question you might ask is, what distance should we use? So in the previous slide, I used the Euclidean distance, which is just the straight line distance. Arguably, you could say that that's the default distance that you would use. However, there are many other distances. Any distance, essentially, is a potential distance measure that we could use for the nearest neighbor classifier. So for example, LP distances, the LP distance between the vector u and v is simply equal to this. Maybe we don't have vectors in RD. Maybe we have strings. So maybe our inputs are a string, is a string of like a word, for example. So another distance we could use is the edit distance. Maybe our data is not in RD. Maybe it's a string of characters, and so the edit distance would say how many additions and subtractions of characters, substitutions are necessary to make my input string equal to any given other string in my training set, and then find the string in the training set that requires the fewest changes to match my input string, and then that would be the nearest neighbor. Correlation distance is another one for signal processing problems. If you want to match signals, you could use a correlation distance between those two signals. So there are many different distances that can be used depending on the problem for the nearest neighbor classifier.